What is the electron configuration for boron with 5 protons, symbol B? Now, by the normal process, things like this are done by strict aufbau. Aufbau is from the German, meaning filling or filling order in order. So in part, we fill shell 1 with 2, and then we use these sort of building stacks, 2, then 6, 2, then 6, 2, then 10, then 6, 2, then 10, then 6, 2, then 14, 10, then 6. And we have these electron subshells. Subshell S is 2, subshell P is 6, and subshell D is 10, subshell F is 14. But as you get through, the subshell F and the subshell D are on inner layers, n-1 and -2. Now, these aufbau rules are strict. As you can see, it's just a numeric table. Second, partial filling is allowed, which is what we will show here. Here you will get 2 filled, and then they'll just use 1 of 6 for boron. Now, the fill order is always, as I said, subshell S first with the 2, subshell F with the 14 if it's there. Obviously, in a small molecule, it will not be. Subshell D with 10, and finally, subshell P with 6. And as I said, subshell D fills with N, but the energy is n-1. And subshell F fills with N, but the energy is n-2. Now, again, these are abstract, just numeric methods and rules you have to decide. What I'm going to try and do is explain this geometrically. All subshells are longitudinal rings of electrons. At the same inclination angle and the same distance, they thereby have the same energy. And they come in 2 hemispheres, with the nucleus, which I show as an oval or a ring, with its axis as the basis. Now, this comes from my interpretation of the Nobel Prize winner Bose in his 1924 proof of statistical mechanics, where he talked about a cylinder surface and 2 times for polarity. Now, my interpretation is different. He used strictly statistical mechanics. But basically, that funny eye that you get in statistical mechanics is the effect of having electrons pulled towards an axis that you don't know what it is. You don't have a frame of reference. Of course, I know the nucleus for this electron. It's not the same place, but I can use that as the frame of reference, and that will change and how I approach subshells. So you can see the example you look at in Wikipedia or any electron subshell you see will be rings as the center of this electron distribution in 2 hemispheres around the nucleus, with electrons along there, but all wanting to be coming into each other, but bouncing off each other. And it is this bouncing off of each other that is statistical mechanics or quantum mechanics. And so until you have a multi-particle off-shell subshell, you do not have statistical mechanics or quantum behaviors. A single electron or a single proton won't do this until you have these multiple sets. Now, my engineering thereby becomes 2 hemispheres and 3 vectors, the main one being this axis. So where the other schedule showed 2, 2, 2, 2, 6, 6, 6, my one hemisphere is 2, then 3, and then a second layer interlaced. Okay, because we're at hemispheres, they're offset by 180 phase, so they can lock into each other tighter at the same count before jumping to the next. So it goes 1, 3, 3, 5, 5, 7, 7, and you can see the path is not quite straight. So the second thing is that obviously the 1 at the poles all line up, but that same shells going out have interlacing, so it's a little different distance. So that shell 7 electron ring with 7 in it is closer and is more like the distance of the 5. So overall, an atomic model is slightly longer than it is at the equator. Along the poles is longer than the equator. And so this looks similar to this logic You still got the arrows flowing from shells to shells, but now I've added this two hemisphere logic because there's a second set exactly opposite this on the other side. And those shells really actually now define geometric 3D engineering places that we can work with to explain these things. And that's what I call the field acceleration physics stack. Now, I then create a diagram that's in 3D. This is different than a Lewis diagram to understand bonding and subshells because I'm building these from the poles 1, 3, 5, 7. 1 plus 3 is 4, and that's the square because that circle at pi r squared is the tightest configuration possible. So 2 hemispheres, and my rule is only full subshells allowed. There are no partials in my method of getting electron configurations. And that's driven by the Bose cylinder surface logic to create quantum mechanics. And so with all the great things that quantum mechanics does, it only happens if you have this cylinder surface for electron subshells. Now, the other thing is I have this a transitional equatorial subshell of 3. You see, these always have 2 hemispheres and they're only full. But what happens with the odd count elements? Well, if you have 3 at the equator, that's an odd number, and you don't have to have a balancing pair. And that's important here for your boron. Okay, so whenever you have systems, you're going to build them in 2 hemispheres, but understand the special logic that a cylinder with 0 distance off the height would only effectively have 1, and that's how we're going to get these odd count electron configurations. Now the polars align, and the preference is always to fill the poles first with the first rule that it's got to be the tightest fit and only full. So what is the electron configuration? And I'm going to show here the Arno-Diagram, and this is the shell 2 template. And remember, that's an either or, because you don't have that inner layer, you don't have the ability to sort of do all the layers that I showed here, which would be a shell 4 and 5 template. Okay, there's only the 2 at 180 degrees, and there's nothing really to make this stable. So either you fill the scrunched cube, okay, or you fill this equatorial for the odd count 3. And in boron, 2 go to the shell 1, then it's full, and 3 are left over, so you get nothing over on this left side, option, and 3 from this. So you have 3 outer shells using the Arno-Diagram shell 2 template. Now this is different from what you're told with the aufbau. The strict aufbau tells you that it's going to be 2s2 after the helium, and then a partial of 2p, 1 of 6. So you're going to have 2 and then 1. Wikipedia says the current thinking is the same. However, the Arno-Diagram tells you that it's helium, then nothing in the S, nothing in the P, S, P, and 3 in the equatorial. The equatorial is always 3. And whichever ones are here are either all full or all empty. Now, why do I think that my method is done? Well, they say boron bonds with fluorine in 3. Specifically, it is triplanar. It's at the same as if 3 things are out there at the equator. Now, Wikipedia says the geometry of the molecule is triangular planar. And this D3H, okay, notice the 3 symmetry conforms to predictions of the Vesper theory. Okay, now, mine is not the Vesper theory, it is the 3D engineering theory. But you can see that if you have 3 electrons that want to be at the shell in shell 2 at the equator, those fluorines which have 1 open space, those 3 will fill. These big black ones are the boron electrons filling the open slot in the fluorine, which is your traditional cube octet, okay? But not the boron. And so you can have a stable boron, a stable boron, a stable boron structure, and the one electron is doing both that as the bond and holding this, this boron here versus the fluorine. So as a result, I believe that I have support for why I believe the electron configurations are for 3 outer shell electrons in an equatorial substrate. So it is helium, then 2 EQ3. Thank you.